Good morning, everyone. Let's continue with the characterless proof. So last week we talked about the complexity issue. So that means complexity is really important. So that means an important thing about algorithm. If we have a more efficient algorithm, it will have a big impact on the performance. So we show the difference. Even we can have better hardware, but if we have a more efficient algorithm, it will have more impact on the performance. So we show the comparisons for this one, right? So this week we finish the another important part about algorithm is the complexity. It's about the characterless proof. Okay, characterless proof. So basically, we already mentioned about if we implement algorithm, first one we need to design the strategies, and then we need to know its complexity. Next one is we maybe even before we do the complexity analysis, we need to know the algorithm itself is correct. But before implementing it, so that means before implementation, we already know we can confirm the catalyst of the algorithm. So of course we can only base on a proof method. That means we prove the implementation is correct. So for here we have two types of proving. The first one we call a partial characteristic proof. So this means as long as we can generate a character result, because we know we do algorithm is like a mapping. So that means we prove every output is correct when the algorithm terminates. Okay, so this one is like has a condition, correct? So that means when it terminates, it is correct. But this is like an assumption. We assume the algorithm will terminate, but if the algorithm or the code, the algorithm will not terminate, we don't know, correct? So this is called a partial characteristic. But if in other way, if we can say we are sure the algorithm will always terminate and will always produce correct results, if like that, that one will be the total characteristic proof. That means the algorithm will necessarily terminate. Necessarily, that means will always, and also will produce correct result. So of course we want to prove this way, correct? It will terminate and will also produce correct results. Okay, and then for the proof, so in fact we have basically three types of proof techniques. Of course, if you want to learn more, you can search mathematic proof. We do have a lot of other things. So we first introduce three here. The first one we call the proof by construction. The basic idea is that we give examples. You can also call it proof by examples. For example, we want to prove something is wrong. We just need to give a counterexample, okay? Or we want to prove something exists, we can just give example. So this is called proof by construction. The other one is called proof by induction. This one is the only example, right? It can prove something existing or something does not exist, but it's not like something else. We want to prove a general case, then it doesn't work. So the other one is called proof by induction. We mentioned this one before. We have base case. Okay. Basically, we have first one is base case. So like a domino game, you first have the first piece, and then of the cards, and then second one is that you have assumption. And the third one is induction. Right? So that means this one is like a k equal to 1, and then k equal to any number, or use n is better. N equal to 1, and then next one we assume n equal to k, the preposition holds, and then we want to prove n equal to k plus 1 also holds. So this one is like a chain. Right? The first case is correct, and then just because of from k to k plus 1 is also correct, because k here is larger or equal to 1. Accordingly, correct, if your problem is case n start from 2, you can just start from 2 first, and then k larger equal to 2. So this one gives one example. That means the initial case, the first one. So because from k we can deduce k plus 1 also holds, and then you can just use this chain to reach the next, and so on and so forth. Here you can reach a general n. Right? So this is called a proof by induction. In fact, our proof method in this course we said is loop invariant. So this one also utilizes the same idea we mentioned before. Maybe there are only minor changes in the steps, but the concept or the basis, the foundation, is just proved by induction. Okay, and then the third one is proved by contradiction. So this one we know, if for example everybody is tall, and then we give an example, give another person which is not tall according to some standard, or everybody is maybe works late, or like this. We can just give an example. We give an example. Somebody works early, not want to work day night, not works late. So just give one example to prove something is wrong. This one is usually just like everything. Everything. So this one is like existing. So if you want to prove something existing, we can use proof by example. You want to prove something is not working for everything, you give a counter example. So this is the idea. But if it's another general case, it's not everything or existing, just like we mentioned before. If you want to prove this one, the summation from 1 to n is equal to n plus 1. It's just one case, correct? So we need to prove this case is correct. But this n, in fact, it can be anything. So that means you cannot list one example. Okay, if n equal to 1, it holds, and n equal to 2, it holds. Like this one. This is called proof by construction. You cannot exhaust all the values of n. So the first one does not work. The second one also does not. Third one does not work, just because you cannot find a number which make this one does not hold. So in fact, we want to prove this is correct rather than just prove this is wrong. Proof by contradiction unit just prove something is wrong. We assume something is wrong, and then we reach a contradiction, correct? So you will assume this is not true. That means not equal to this one. Then you need to give an example which make this one does not hold. So that means does not equal. So how can you find that example? In fact, the result is correct. So that means it's not possible as well. Or you can think about it. Yeah, if you prove this is wrong, and then you will have a contradiction. So I think that's the main thing. You cannot find any contradiction. Maybe. So how easily find that contradiction? So left is not equal to right. What's the contradiction? So left is not equal to. Yeah, you still need to prove left is still equal to right. left equal to right. You said left is not equal to right, then you have reached some contradiction. Maybe one is just easily to find, is left is equal to right. That one has a contradiction to the assumption. Why is it wrong? Just because you have wrong contradiction, a wrong assumption. Then we need to say this one is wrong, then the other side is true. So that one you proved L equal to right, left equal to right. So this is an indirect method to prove something. Yeah, for some cases it works, but for this one, yeah, it's still better to utilize this proof by induction. We assume any case it is true. Okay, proof by induction based on this one. Base case, when equal to 1, it holds because left is equal to 1 plus tier 1. Okay, so just tier 1 left equal to 1. Right is 1 multiplied by 2 over 2 is 1. So left equal to right. So the first case holds. Okay? So base case holds. And then assumption is n equal to k, it will hold. So that means you can just write it out. Okay? So that one will be, okay, let me write here. So 1 plus 2 plus k equal to k plus 1 and then 2. So that's the assumption. Okay? So that means this one is the holds. And then how to prove the last one? Okay? The last one we said is induction. Okay? So this one is also not hard to prove. Why? Because you have this assumption is correct, and then you prove n equal to k plus 1 also hold. So you can just substitute n equal to k plus 1. So left is equal to 1 plus 2 plus tier k and k plus 1. Okay? So this is the previous item, this is the last item. So this one is already know because 1 plus k is equal to this one. You substitute. So you have this one. So for this one, the method is just we prove from left you reach the right. Okay? We can also prove left to some middle and the right to the middle, and then they reach together. So they are equal. But here is very simple, so we don't need to do that complicated steps. So you factor out k plus 1, and then what you will have. Okay. So this one is k plus 1, and then 2k plus 2. K plus 2 is what? Is k plus 1 plus 1. So exactly what? The right hand. Okay? So because right hand is also this one. Okay? You just substitute right is also equal to n, because n is already k plus 1, you substitute this one, and then you have 2k plus 1 n substitute by k plus 1 and then 1. So you have left equal to right. So you also prove. And then by induction we proved in the end, you say like this: by induction we prove, then hold. Okay? So this is the proof by induction. So basic idea is that we follow the proof by induction steps. We first do the base case, and then assumption, and then the induction. In fact, our our method is the same as this one, but the only difference is the last step. Okay, later we talk about. So in fact we combine the case 2 and the case 3 together, and then we add another step 4 to prove the conclusion. That means our proposition is true. Okay, when we talk about that loop invariant based proof, we compare the difference. We may go back to here again. Okay, let's continue with the proof by induction. Okay, proof by loop invariant based proof for algorithm proof. And then for this one, we have 3 steps. So the first one is initialization, second one is maintenance, third one is termination. In fact, initialization is exactly the same like the previous one, base case. Okay, base case. And the maintenance, in fact, it includes the 2 steps, is the assumption and also induction. Okay, the last case is new. Okay, that's the case is new. Let's look at it one by one. Okay. So this one we said logic expression with the following properties. We first do the first initialization. So for this one, we want to mention the loop invariant is dealing with the loop, not dealing with the whole part, but it will be used. Basically, we use this one to prove the loop is correct, but we use this loop invariant method to prove the whole algorithm is correct, because for other steps we mentioned before, you can check, you can confirm directly. For example, you accept input, you do output, because in between is the loop, correct? So the most important part is the loop. The loop, we don't know whether the characteristics will always hold when we are going through the loops. So this is the reason we want to use the loop invariant based method to prove the whole catalyst is verified. Okay. So the first one we set the initialization. This one means before we start the loop, it is correct. That means we approve this. Yeah, we reach here. The status is okay. The status is correct. The catalyst is guaranteed. So that means at least before we start the loop, it is correct. And then we want to prove after the finish the loop. After we finish this loop, it's still correct, and then we can prove the rest. Correct? That's easy. So this is the first step. Usually for this one is a lot harder to do. So, but we need to be careful. So initialization means before you start do anything. Correct? Before you start do anything means, for example, if we have a loop like a for I equal to 1 and I less than 10 and then I plus like this one. This means before you start to check I is less or equal to 10, before you do that one, but you have done the first one because that's the start of the loop. You will test whether the first step is whether I is less or equal to 10, correct? But you will do the assignment, and then if I is this one, you will go to loop. You will continue the loop, correct? The loop content. So we need to know we have done the first statement, okay, the first assignment, but we haven't checked the condition, correct? Check the loop condition. Okay, this is the thing we need to be clear. And then the most important part is the second step. So this one is maintenance. So this means it will remain true. It will always true. Can remain true after we finish one loop. Or you can say in another word, it is true before an iteration of the loop. It is still true after finish the iteration. So this means before we started the loop, it is true, and then after we finish the loop, it is still true. That means we guarantee this loop iteration does not change the catalyst of the algorithm. Okay? So this is the idea. Does not change. So that means after finish one loop, because this one loop is general, this is the same as our previous induction, proof by induction. So that means after finish, we assume k is correct, and then after finish this loop, that means we are ready to do the k plus 1. Okay? Because we finish this one, it will reach the beginning of the next loop, next iteration. So that means before we finish the case iteration, it's correct. After we finish the case iteration, it will reach the beginning of the k plus 1 iteration. It is still correct. So it is ready to continue for the next iteration. Because we proved the general case, k can be anything. So last time when k equal to k plus 1, of course not a k equal to k, n equal to k plus 1, not a k, n equal to k, it will go with the same process. So it will reach the k plus 1 in the end, finish the k plus 1 iteration. That one will be the start of the k plus 2. Right? So that the end of one iteration will be the start of the another next, okay? Another or next iteration. So this is the proof by induction main steps. Okay? So the assumption and the induction. So that means we combine these two steps together as the maintenance. Okay, as the maintenance step. So that means these three steps all together is the same as the previous one, proof by induction. Okay? First case initialization, and then assumption n equal to k is correct. That means at the start of the next iteration, it is correct, and then remain true before the next iteration. That one will be this one, correct? So when we finish the k iteration, that one will be the start of the k plus 1. So that means the k plus 1 is also correct. So in fact we join these two together, correct? So that means of course we are looking at the start. For that case is start. For this case is like the itself step. So maybe there's some minor difference, but the idea is similar, correct? So whether you prove the start or you prove finish the end. So in fact, because the end of the one step is the start of the next one. So this is the same idea, correct? Same idea. Okay. So that means we have this Siemens already utilized the proof by induction. So the last one, in fact, the new things, because your target is proof the catalyst of the algorithm. So for this one, we need to reach the goal. We need to clarify the goal has been met. So this one, we said we finished this one, initialization, maintenance. In fact, the proof is almost done. The last step, in fact, is harvest. It is harvest the steps, harvest the step, because you have half the proof. So this one basically is just like based on the previous loop invariant. You have done the proof. It will maintain. It will keep correct after finish the loops, the iterations. Then we give you a good property. When the loops finish, when the loop finishes, it will give you, it will already directly reach the proof. The preposition is true. So this is when the loop terminates. The invariant, in fact, before you do this one, we didn't mention that one, but when we talk about the real proof, we'll give you example. You must give a loop invariant statement first, because your proof is centered that loop inferent, around that loop inferent. If you don't have a loop inferent, what to prove? You need to first design a loop inferent. That loop inferent will always remain true during the whole iterations. Okay. So the invariant means the loop invariant, along with the vector that loop terminates. So this means when the loop was finished, for example, we still use this case. What will be the case when the loop will finish? What is the value for I now? I is equal to 1, and then I less or equal to 10, I plus plus. So every time you increase I by 1, of course excluding the first case, so I equal to 1 first, and then you test. So it's like this one. So I equal to 1, and then this one, and then next one will be I plus plus. So next one will be I will go to here. So I equal to 1, I less than or equal to 10. So we enter the loop. After finish the loop, we increase I by 1, and then we test I whether it is still less or equal to 10. And then if it is yes, we continue. For after finish the loop, we increase I by 1 more, so on and so forth. So only after you increase I to be a number, to reach a number which is larger than 10, it can exit. So this is I equal to 10, that's the step, equal to 10 after increase by 1. For example, first one is I equal to 9, increase by 1, it's 10, and then it's still less or equal to 10. So because it's equal to 10, so we continue. After finish, we increase I equal to I plus 1, which is 11. 11 is not less or equal to 10. Then we exit. So after finish the loop, I is equal to 11. So it's one more than the bound. So this one will give us a conclusion, because you will substitute this value to the loop invariant, because your loop invariant is like in the beginning of the ith step or iteration. Okay, you need the pattern is like this one in the beginning, because you need to prove this initialization. In the beginning, before you start the loop, before you finish, in the beginning of the ith iteration, we have what? This one. That's the content. So this one you will substitute I equal to 11. So you are in the beginning of the I equal to 11. That means 11th, because you have finished 10 iterations. Now it's in the beginning of the 11th iteration, but it cannot do the loop because loop content, because it does not meet the condition. But you just substitute I equal to 11, and then in the middle, maybe it's like maybe, for example, like our previous example is 1 plus maybe I n equal to like this one. So you substitute n equal to I plus 1. The I equal to the n is like the iteration. The 11, for example, like 11 here. And then you will prove that case, the 1 plus 2 plus 11 equal to 11 by 12 over 2. So that's maybe the proof you want to have, because your case is just reach 10, so that means you will prove that result. Okay. So when we talk about the case, you will find this trick, clearly. So it will just proved. So gives the useful property. So you just so last step you just substitute I equal to that value, and then a useful property that helps show the loop is cut. So that means I've finished the loop, it is still cut. So these are similar to the mathematical induction, means proof by induction. The difference we mentioned, cut. So we combine the second and third steps into one, but also have some difference, minor difference, and we add a new step, which is this one. The new step, you can just do substitution of the loop iterator cut into loop inferent. Loop inferent is a statement, and then you substitute that loop iterated value. It will just produce a statement. That statement, in fact, is the catalyst proof conclusion. Okay, so that means you prove the loop is cut, and then you can finish other contents of the algorithm is also cut. Okay, this is the basic logic of this method. Just like we have this initialization, maintenance, and termination. So every loop inferent based proof, you need to have these three steps. But in fact, many students will forget to give a loop inferent statement. So this is is not a good cut, because if you don't have loop inferent, how to prove? You prove what? So this is the first mistake. The second mistake is that many people will do just like the explanation instead of proof. The person who want to prove will just explain the pseudocode rather than prove based on these steps. That's even bad, even worse. Because this one, proof by loop inferent based proof, must follow these three steps, because this guarantees. This one will guarantee the catalyst of your proof. If you don't follow these steps, we don't have that method proved. We don't know whether it is true or not. So based on this one, you must have these four steps. The first one, give a loop inferent. Second one, initialization. Before the start of the first iteration, it is true. And then you combine the second and third steps of proof by induction into the maintenance. Means in the beginning of the current iteration, it is true. After finished that iteration, it was true. You may ask me how to prove this one. Then you need to go through the loop contents. Loop contents will validate or re-establish the catalyst of the loop. Okay, the algorithm. So we go through the loop contents to prove this one remain true, because this one is not like a formula. We can utilize that substitution and k plus 1. So here we can only go through this loop contents. We said, okay, after finish this loop, it is still true. We need to go through the steps of the loop in the loop. So after finish this one, then you said this is general case, because this one is like for every loop, it will remain true. And then you just need to give when the last step, when the loop finish, what is the value of the loop iterator? Loop, you will have an iterator, so loop iterator, because that iterator will be here, ith loop. So I is equal to what when the loop finished, and then you substitute the I into the loop invariant. So the last step is easy. I loop invariant, you get the proof. That's it. First step unit is also easy, So you check before the loop, before anything, before doing any loop contents or condition check, okay, you only do the first assignment. That one, because that one is like initialization, so that's why I call it loop initialization, okay, loop inference initialization step. So only finish the initialization means set the value for the iterator, and then you check the proof, check the catalyst of the algorithm, it's correct. Okay, this is the idea, and then we'll continue with the examples. So for example, for here, we are not give a detailed example for this one, but I'll give you a rough idea, and then we give you detailed proof for the next one, okay, to save our time. So this one is a catalyst proof of linear search. We have finished the linear search pseudocode cat before. It is very simple, which is here. So you search for key in a sequence of A, and then you first initialize I, the first item. We start from 1, I equal to 1, and then you do a while loop. As long as you do not reach the end, you just compare with the element and the key. If they are not equal, so you continue with the next item, right? Move the pointer to the next, or move the index, increase the index by 1. And then if we finish the loop, we have two cases. First one, we reach the end, beyond, we didn't find it. The other one is we are still in the sequence, we didn't go beyond the end, and then we find it, okay? So the first case we didn't find it, second case we find it, okay? Find it in any location, even in the end, but we didn't go beyond, okay? Because if we found, then this one does not hold, okay? This one does not hold means this condition does not hold, it will exit, okay? The other one is that you found it, and then, but yeah, anyway, it will return. But if it didn't find it, it will test this one, okay? Test this one. So that means I is not equal to, not less or equal to n, is go beyond n. Then this one does not hold, so also will exit. So either condition will exit. The first case exit means didn't find it. The second case we find it. Okay, we find it. Okay, and then for this one, then we test. Okay, if is within range is true. If is out of range, which means false. So we test it. So this one we have the proof, okay, like this. So the first thing is that we need to design a loop inferent, the LI. You can write it like LI, no problem. People can understand loop inferent. So loop inferent, what will be loop inferent? So this loop inferent is a statement. It must be true, correct? The statement will be true in the beginning of the iteration, okay? Iteration. So we write like this one. So before we do this condition, what will be true? What will be true? So because this one is ready to search the eyes, okay? Ready to compare the AI, whether AI is the key or not. But when you reach here, you have already exhausted all the elements before AI. That means 1 to I plus 1. Okay? So just because you haven't found the key in the previous I plus 1, I minus 1 elements, then you will go with the AI. Okay? So your statement must be like this. Okay, in the beginning of the ith iteration, or the next while loop, you haven't found the key in front. Okay? In front means you just give the detailed information. You said you haven't found a key in the previous sequence. Okay? Key does not belong to A1 tier AI-1. So that's the idea. Okay? So at the start of each iteration, here is the ith iteration. Okay? The search key that contains you want to find, okay? The search key is not in the subarray A1 tier I-1. Okay? So that means just because we haven't found the key in the previous elements, then we need to go with the next one. If we already found it, we will not continue with the next one, because you found it. You only need to find one. We don't say we want to find all the appearances. Okay? Only one appearance, and then we exit. We just find out whether key is existing in the sequence. If it exists, in the array A, then return the true. Otherwise, return false. Just check whether it exists. We only want to find one experience one time. Okay? So this is the loop invariant. And then next step, so that means initialization. Initialization means I equal to 1. Okay? So let's write like this. We don't want to give a detailed step, but give you the so initialization. Write this out. Initialization. Before you start the first iteration, so you test, okay? Because you want to check before the initialization step is true. Means at the start of the first iteration, just go through this one, examine this one, and I equal to 1. Okay? At the start of each iteration, the I equal to 1. At the start of the first iteration of the while loop, I equal to 1. Because so you substitute at the start of the first iteration of the while loop, the search key is not in the subarray, which is I equal to 1. That one will be 1 tier 0. 1 tier 0. Start from 1 tier 0. This one must be larger than 1. No. This one is equal to empty. Okay? So that means we find the subarray. This one subarray will be empty. Of course, a key does not belong to empty, because empty set doesn't contain anything. Key is a value. Of course, key does not belong to an empty set. So this one is true. Okay? That's why it's not in. Okay? Not in here. Not in. So that means the loop invariant holds. Okay? So initialization step proved. And then the maintenance step. Maintenance step need to prove at the beginning of the next iteration the loop invariant is true. After finish this iteration is still true. So let's just give oral explanation for this one. So at the beginning of this iteration is true. That's our assumption, correct? Because at the beginning that will be the elements of A from 1 to I minus 1 based on the by loop invariant. At the beginning of the I plus 1, the ith iteration, I equal to I. Okay? It's not I minus 1. At the beginning of the ith iteration, it holds because by induction. So at the beginning of the ith iteration, that's you substitute at the start of the ith iteration of the while loop, the search key is not in the subarray. So A1 tier I minus 1 does not contain key. Okay? This is by induction, by loop invariant. And then we want to check the next one. Okay? So we want to say after finish this while loop, whether it is still hold. So we have the case. So the ith iteration, we have I equal to I, cat. Now n is equal to I. So that means the ith iteration. So we have two cases because you increase the I, increase I. So if the first case does not hold, I is less or equal to n, then we can substitute. So that means we can substitute I equal to something. We have this case, so it's not meet this one, then of course not existing in the array A. If it is equal to this one, we can also give a result, or we can revalidate the previous loop invariant. So this is just need to confirm this one. If it does not equal to this key, and then I will be increased by 1. So I is increased to I plus 1. Plus 1. Of course, I equal to I plus, then from 1 to I does not hold. So I equal to I plus 1. You will get 1 to I. And then you also prove the next step. At the start of I plus 1 iteration, the search key is not in the array A 1 to I plus 1 minus 1, which is I. So this is the maintenance. And then in the termination, you just said after we finish this loop, we have two cases. I is less or equal to n, or I is larger than n, which is n plus 1. So either key, if n plus 1, then means key is not in the array. If I is less than or equal to n, means it is in the array. Is in the array. That means this one holds. So that's the termination. Okay, because we don't want to spend much time on this example, we want to look at the insertion sort. So when we talk about this one, we do this type of steps again in that example. Okay. So we go through the insertion sort. We use the insertion sort to prove this, to go through these steps one by one, and then in detail. So you can find the proof in the page 18 to 20 in the book, or you can just go through the slides. So we'll continue with the slides to check the whole steps in the next slides. Okay, let's first release these slides, and then we continue for the next.